what came before everything, before the stars, before the galaxies, before space and time themselves? This question has haunted humanity for millennia, but only recently have we glimpsed an answer so profound it changes everything. Imagine a moment when the entire universe was smaller than an atom, infinitely dense and impossibly hot. Then, in an instant that defies imagination, it began to grow. You and I are going to journey back to that moment, to the very beginning of time itself. Are you ready to witness the birth of reality? Take a deep breath and let's travel together to the edge of understanding. Every culture throughout human history has asked the same fundamental question. How did all of this begin? The ancient Greeks imagined chaos giving birth to order. Eastern philosophy spoke of cycles without beginning or end. But what if the answer was stranger than any myth we ever created? What if the universe itself had a birthday, a precise moment when it came into being? For most of human existence, this question belonged to philosophy and religion. Science seemed powerless before such cosmic mystery. Yet in the 20th century, something remarkable happened. We discovered that the universe is speaking to us, whispering its origin story in the language of light and mathematics. Think about this for a moment. Right now, as you listen to these words, you are made of atoms. Those atoms were forged inside stars that lived and died billions of years ago. But where did those stars come from? And what came before them? When you trace the thread backward, following the chain of cause and effect, you arrive at something almost impossible to comprehend. You arrive at a moment when there were no atoms, no stars, no galaxies. A moment when everything that would ever exist was compressed into a space so small it makes a grain of sand look like a galaxy. This is where our journey begins. The story we are about to explore is not just a scientific theory. It is the story of you. The Big Bang Theory tells us that every atom in your body, every thought in your mind, every moment of your existence traces back to that first moment. You are not separate from the universe. You are a way the universe has organized itself to become conscious and look back at its own origin. Does that fill you with wonder? It should. Because what we are about to discover is that the universe is far more magnificent and mysterious than we ever imagined, and you are an integral part of its unfolding story. Before we journey to the beginning, we need to prepare our minds for what lies ahead. The Big Bang is not an explosion in space. It is the expansion of space itself. This distinction is crucial. Imagine the universe as the surface of a balloon being inflated. Every point on the surface moves away from every other point, not because anything is moving through the balloon, but because the balloon itself is growing. Now imagine that balloon in reverse, shrinking down and down until all of space, all of matter, all of energy converges to a single point. That is where we are going. You might wonder how we could possibly know what happened at the beginning of time. Were we there to witness it? It's not. Of course not. But the universe has left us clues, breadcrumbs scattered across the cosmos that tell us exactly what happened and when. We have learned to read these clues with exquisite precision. The light from distant galaxies, the faint whisper of radiation filling all of space, the abundance of different elements, all of these are like fossils from the early universe. They tell us a story so detailed and so compelling that we can reconstruct the first moments of creation with astonishing accuracy. Let me tell you something that might change how you see everything around you. The screen you are watching this on, the air you breathe, the ground beneath your feet, none of this existed in the beginning. There was no matter as we know it. There were no atoms, no particles, no structures of any kind. There was only energy, pure and undifferentiated, existing at temperatures so extreme that nothing familiar could survive. From that formless energy, everything you see and touch would eventually emerge. No. How does formless energy become stars and planets and people? That is the story we are about to unfold together. As we prepare to journey backward in time, I want you to release any preconceptions you might have about what is possible or impossible. The early universe operated under rules so different from our everyday experience that our intuitions will fail us. Time itself behaved differently. Space was not the vast emptiness we know today. Cause and effect blur at the boundaries of the beginning. Are you feeling a sense of vertigo? That is appropriate. We are about to step outside the universe as we know it and glimpse something more fundamental, something that existed before existence itself. Let us begin our descent into the deepest mystery. The journey we are about to take will last 1 hour of your time, but we will travel back more than 13 billion years. We will witness events that lasted mere fractions of a second but shaped everything that would ever exist. We will see the birth of matter, the forging of the first atoms, and the moment when light finally broke free to travel across the universe. Every step of this journey has been mapped by brilliant minds working to understand our cosmic origins. You and I are going to walk in their footsteps, guided by evidence and inspired by wonder. The greatest story ever told is about to unfold. What does it mean to say the universe had a beginning? This question troubles our minds because everything in our experience comes from something else. Trees grow from seeds, humans are born from parents, stars form from clouds of gas. But if the universe itself had a beginning, what came before? This is where we encounter the edge of scientific knowledge and enter a realm where language itself begins to fail. Some scientists speak of quantum fluctuations in a primordial vacuum. Others suggest our universe is one bubble in an eternal multiverse. But the truth is, we do not know what came before the beginning, or if that question even makes sense. Let us approach the concept carefully. Imagine time itself as a dimension, like a road stretching from the past into the future. Now imagine traveling along that road backward, watching the universe grow younger and denser as you go. Stars disappear back into gas clouds. Galaxies merge and compress. The universe grows hotter and smaller. You keep traveling backward, and the universe keeps shrinking until you reach a moment approximately 13.8 billion years ago. At this point, the road ends. Not because something blocks your path, but because the road itself does not exist beyond this point. Time begins here. This is profoundly strange. We are accustomed to thinking of time as eternal, stretching infinitely in both directions. But the Big Bang Theory tells us that time itself was born. Before this moment, there was no before. The question of what happened 1 second before the Big Bang is meaningless in the same way that asking what is north of the North Pole is meaningless. Time and space came into existence together as part of the same cosmic event. Does your mind rebel against this idea? That is because we are confronting something truly outside our everyday experience. We are looking at the boundary of reality itself. Scientists use a word to describe the state of the universe at the very beginning. They call it a singularity. A singularity is a point where the normal rules of physics break down, where quantities like density and temperature become infinite, where our equations stop working and return nonsensical answers. It is not a place or a thing. It is more like a boundary, a limit to what we can know and describe with our current understanding. Imagine trying to measure the temperature of an infinitely small, infinitely dense point. The very concepts we use to describe reality fail us here. Does a singularity actually exist? Or is it a sign that our theories are incomplete? Most physicists suspect the latter. Our best theories of gravity and quantum mechanics both work wonderfully well in their own domains, but they give contradictory answers when we try to apply them to the very beginning of the universe. What we need is a theory of quantum gravity, a way to describe how space and time behave at the smallest possible scales. Until we have that theory, the exact nature of the initial moment remains shrouded in mystery. But do not let this uncertainty trouble you. What we know for certain is already astonishing. We know that approximately 13.8 billion years ago, the universe was in a state utterly unlike anything we observe today. All the matter and energy that would ever exist was compressed into an incredibly small volume. Temperature and density were almost beyond comprehension. The universe began to expand. Not into empty space, because there was no empty space outside the universe to expand into. Rather, space itself began to grow, carrying matter and energy along with it. This expansion continues today. We can measure it. We can trace it backward in time. And when we do, we arrive at the beginning. Why did the universe begin? Why did it expand rather than remain static? These questions push us to the very edge of scientific inquiry and into the realm of philosophy. Some scientists propose that universes are constantly being created through quantum processes we do not yet understand. Others suggest that our universe is part of an eternal cycle of expansion and contraction. Still others argue that the universe simply is, and that asking why is like asking why mathematics is true. We may never know the ultimate answer, but we can know what happened once the expansion began, and that story is extraordinary. Before we move forward to witness the first moment of time, let us pause and appreciate where we stand. You are a conscious being, made of atoms, living on a planet orbiting a star in a galaxy containing hundreds of billions of other stars. And all of this, every bit of it, emerged from a state of pure potential. The fact that we can even ask questions about the beginning of time is itself a kind of miracle. The universe has evolved in such a way that part of it has become conscious and curious about its own origins. You are that curious part. You are the universe knowing itself. Let us continue. We are about to witness something no human eye could ever see. We are going to the very first moment of measurable time. Scientists call this the Planck Epoch, named after Max Planck, the physicist who discovered quantum mechanics. This era lasted from time 0 to approximately 10 to the negative 43 seconds after the Big Bang. Does that number mean anything to you? Let me put it in perspective. A Planck time is 0.00000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 1 second is compared to all the time that has elapsed since the Big Bang. During the Planck Epoch, the universe was so small, so hot, and so dense that all 4 fundamental forces of nature were unified into one. Gravity, electromagnetism, and the strong and weak nuclear forces all behaved as different aspects of a single superforce. Imagine a world where all the rules of physics were different from anything we can observe today, where quantum effects dominated on cosmic scales, where the distinction between space and time was blurred or perhaps did not exist at all. So, this is not science fiction. This is the real history of our universe, though it is a history so strange we can barely imagine it. What would you see if you could somehow observe the Planck Epoch? Nothing familiar. There were no particles, no atoms, no light as we understand it. The energy density was so high that the distinction between matter and energy was meaningless. Everything that would later become everything was present, but in a form utterly alien to our senses. The temperature was approximately 10 to the 32 degrees. That is a 1 followed by 32 zeros. Nothing that exists today could survive even a fraction of such heat. At these temperatures, even the vacuum of space boils with creation and destruction of virtual particles. Our current physics cannot fully describe what happened during the Planck Epoch. To understand it properly, we would need a complete theory of quantum gravity, something that unites quantum mechanics and general relativity. Many brilliant physicists are working on this problem right now. String theory, loop quantum gravity, and other approaches all attempt to peer into this earliest moment. But for now, the Planck Epoch remains partly mysterious. It is a reminder that despite all we have learned, there are still profound puzzles at the heart of existence. Does this humility in the face of mystery make the story less compelling? Not at all. It makes it more human. As the universe expanded during the Planck Epoch, it also cooled. This might seem counterintuitive. How does expansion cause cooling? Think of a compressed gas. When you allow it to expand, it cools down. The same principle applies to the universe itself. As space expanded, the energy within it was spread over a larger volume and the temperature dropped. This cooling would have profound consequences. As the universe cooled, the unified superforce began to separate into distinct forces. First, gravity split off from the others. This was the first major phase transition in cosmic history, a moment when the rules of reality fundamentally changed. Why does this matter? Because when gravity separated from the other forces, it meant that space-time itself became a distinct entity, subject to the warping and curving described by Einstein's general relativity. Before this moment, our very concepts of space and time were not applicable. After this moment, the universe had a structure we could begin to recognize. It was still unimaginably different from today, but it had taken its first step toward becoming the cosmos we inhabit. You are witnessing the birth of geometry itself, the moment when space and time acquired the properties we rely on to understand reality. Think about the implications for a moment. The space you occupy right now, the time through which you move, these did not exist in their current form before the Planck Epoch ended. The stage upon which all of reality plays out was constructed in those first, inconceivable fractions of a second. Every event that has ever happened, from the formation of the first star to the moment you were born, has taken place on a stage built in that earliest moment. Does this make you see space and time differently? Thus not eternal and unchanging, but as emergent properties of our universe with their own origin story? The Planck Epoch ended when the universe was about 10 to the negative 35 meters across and had cooled to around 10 to the 27 degrees. Still unimaginably hot and dense, but cool enough that the forces of nature began to differentiate. Cool enough that space and time acquired definite meaning. Cool enough that the universe was about to enter its next phase, an episode of expansion so rapid and so dramatic that it would set the stage for everything to come. We call this episode inflation, and it is one of the most astonishing ideas in all of cosmology. Let us witness it together. What I am about to describe is so extreme that when it was first proposed, many scientists thought it was impossible. Between 10 to the negative 36 and 10 to the negative 32 seconds after the Big Bang, the universe underwent a period of expansion so rapid that it doubled in size every tiny fraction of a second. In less time than it takes light to cross an atom, the universe expanded by a factor of at least 10 to the 26. Imagine a coin suddenly becoming larger than the observable universe. That gives you some sense of the scale of inflation. Did this happen? What could cause such extraordinary expansion? The answer involves something called an inflaton field. Think of a field as something that exists everywhere in space, like the electromagnetic field or the gravitational field. The inflaton field had a special property. When it was in a high-energy state, it created a kind of repulsive gravity, a force that pushed space apart. During the inflationary epoch, this field was stuck in that high-energy state, like a ball balanced on top of a hill. And while it remained there, the universe expanded exponentially. This might sound like science fiction, but inflation solves several profound problems in cosmology and makes predictions that have been confirmed by observation. What problems does inflation solve? Before inflation was proposed, cosmologists were puzzled by several observations. The universe appears remarkably uniform in all directions. Regions of space that are so far apart they could never have influenced each other, nevertheless, have almost exactly the same temperature and properties. Could this be? Inflation provides an answer. Before inflation, all these distant regions were close together, in contact and able to reach the same state. Then, inflation stretched them apart faster than light could travel between them. They remain similar because they came from the same small patch of space. Inflation also explains why the geometry of space appears flat rather than curved. Imagine the surface of a balloon. When the balloon is small, its curvature is obvious. But if you inflate it to enormous size, any small patch of the surface appears flat. Inflation inflated the universe so much that even though space might have overall curvature, the observable portion appears flat to our measurements. It is like standing on Earth and perceiving it as flat because we can only see a tiny portion of its total surface. Inflation took whatever curvature existed and smoothed it out beyond our ability to detect. But inflation did something even more remarkable. During this period of explosive expansion, quantum fluctuations in the inflaton field were stretched to cosmic size. These tiny quantum jitters became the seeds of all the structure we see in the universe today. Every galaxy, every star, every planet exists because of quantum fluctuations that occurred during inflation. Think about that. The device you are watching this on exists because of a quantum fluctuation that happened in the first tiny fraction of a second after the Big Bang. You exist because of those fluctuations. Quantum mechanics, operating at the beginning of time, shaped the large-scale structure of the universe. How do we know inflation really happened? We can see its fingerprints in the cosmic microwave background radiation, the faint glow of light left over from the early universe that fills all of space. The pattern of tiny temperature variations in this radiation matches precisely what inflation predicts. The statistics of these variations, their size and distribution, all agree with the inflationary model. More recently, scientists have been looking for gravitational waves created during inflation, ripples in space-time itself that would provide even stronger confirmation. The search continues, but the evidence for inflation is already compelling. Inflation ended when the inflaton field finally rolled down from its high-energy state, like a ball rolling down a hill into a valley. As it did, all the energy stored in the inflaton field was converted into matter and radiation. This was the reheating of the universe, a moment when the universe was flooded with particles and energy. The temperature soared back up, though not to the extreme levels of the Planck Epoch. This is when the universe, as we recognize it, filled with particles and forces interacting according to the laws of physics we can test, truly began. The stage was set for matter to form and for complexity to emerge. Think about what just happened in this inconceivable sliver of time. The universe expanded from smaller than an atom to larger than a grapefruit. Quantum fluctuations were amplified into cosmic structures. The seeds of every galaxy were planted. Space was smoothed and flattened, all in less than a trillionth of a trillionth of a trillionth of a second. And now, as inflation ended and reheating began, the universe was ready for its next chapter. It was time for matter itself to crystallize out of pure energy, for the first particles to appear and begin their journey toward becoming stars, planets, and eventually us. Let us watch as matter is born. As the universe emerged from inflation and reheating, it was filled with a searingly hot soup of fundamental particles and energy. This was the Quark Epoch, lasting from about 10 to the negative 12 seconds to 10 to the negative 6 seconds after the Big Bang. During this time, the universe was too hot for protons and neutrons to exist. Instead, it was filled with their constituents, particles called quarks and gluons, along with electrons and other fundamental particles. All of these particles were constantly being created and destroyed, popping in and out of existence as energy converted to matter and back again according to Einstein's famous equation. What are quarks? They are the fundamental building blocks of matter, the particles that combine to form protons and neutrons. There are 6 types of quarks with whimsical names given by physicists: up, down, strange, charm, top, and bottom. In the Quark Epoch, these particles moved freely through space, unable to bind together because the temperature was too high. They were held together by gluons, the particles that carry the strong nuclear force. The entire universe was essentially one gigantic particle accelerator, far more powerful than anything we can build on Earth, where particles collided at energies we can only dream of recreating. Why is this period called an epoch? Because it represents a distinct era in cosmic history when the universe had particular properties. During the Quark Epoch, matter and antimatter existed in nearly equal amounts. For every quark, there was an antiquark. For every electron, a positron. When a particle met its antiparticle, they annihilated each other in a burst of energy. And then that energy could create new particle-antiparticle pairs. The universe was in a kind of dynamic equilibrium, with matter and antimatter being created and destroyed countless times every instant. But there was a subtle asymmetry, and that asymmetry would prove crucial. The asymmetry between matter and antimatter is one of the deepest mysteries in physics. For every billion antiparticles, there were 1,000,000,001 particles. This tiny excess, just 1 part in 1,000,000,000, meant that when most of the matter and antimatter annihilated each other, a small amount of matter remained. That leftover matter is everything we see today. Every star, every planet, every atom in your body exists because of this tiny imbalance in the early universe. Without it, matter and antimatter would have completely annihilated, leaving only energy. The universe would be filled with light but no substance. What caused this asymmetry? We do not know for certain. This is one of the great unsolved problems in physics. The laws of physics as we currently understand them predict that matter and antimatter should be created in exactly equal amounts. Yet clearly they were not. Some process in the very early universe must have created slightly more matter than antimatter. Understanding this process is a major goal of modern physics. It is a reminder that our story of the Big Bang, while detailed and well supported by evidence, still has gaps, still has mysteries waiting to be solved. And that makes it even more compelling. As the universe continued to expand and cool during the Quark Epoch, another important transition occurred. The strong nuclear force, which had been part of the unified electroweak force, separated and became distinct. Now, all 4 fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, were operating independently. Each force had its own character and ruled over its own domain. Gravity shaped the large-scale structure of space. Electromagnetism governed how charged particles interacted. The strong force bound quarks together, and the weak force mediated certain kinds of radioactive decay. The universe now had all the forces it would need to build complex structures. Picture the Quark Epoch as a cosmic forge, impossibly hot and dense, where the raw materials of reality were being prepared. Quarks and electrons and neutrinos, all the fundamental particles that would eventually combine to form atoms and molecules and life, all existed freely in this primordial soup. The universe was opaque during this time. Light could not travel far before being scattered by the dense plasma of particles. If you could somehow stand in the Quark Epoch, you would be surrounded by a blindingly bright fog, unable to see more than an infinitesimal distance in any direction. But you would be standing at the birthplace of matter. The Quark Epoch ended when the universe cooled enough for quarks to bind together permanently. This happened at about 1 microsecond after the Big Bang, when the temperature dropped to around 10 trillion degrees. At this point, quarks combined in groups of 3 to form protons and neutrons. This transition is called the Quark-Hadron transition, and it was another pivotal moment in cosmic history. Suddenly, the universe was no longer filled with free quarks, but with composite particles that would become the nuclei of atoms. The building blocks of all ordinary matter had finally stabilized. The universe was ready for its next transformation. With quarks now confined inside protons and neutrons, the universe entered what we call the Hadron Era. Hadrons are particles made of quarks, and they now dominated the mass and energy of the universe. But the story was far from over. The universe was still far too hot for these protons and neutrons to combine into atomic nuclei. Instead, they bounced around in a dense soup, colliding with photons and other particles. Meanwhile, electrons, muons, and neutrinos, collectively called leptons, were also abundant. These two families of particles, hadrons and leptons, gave this period its character. It was a time of intense activity and interaction. During the Hadron Era, matter and antimatter were still annihilating each other. Protons and antiprotons, neutrons and antineutrons, electrons and positrons, all were creating and destroying each other in a cosmic dance. But remember that tiny asymmetry we discussed? It meant that for every billion annihilations, one matter particle survived. Slowly but surely, antimatter was disappearing from the universe, leaving only the small excess of matter behind. By the end of the Hadron Era, about 1 second after the Big Bang, almost all the antimatter was gone. The universe was committed to being a matter-dominated universe, the only kind of universe where structures like galaxies and life could form. As the universe continued to expand and cool, the Hadron Era gave way to the Lepton Era. This happened when the universe was about 1 second old and had cooled to around 10 billion degrees. At this point, protons and neutrons were no longer being created from energy. The temperature was too low. But electrons and positrons were still abundant, and they continued to annihilate each other. The energy density of the universe was now dominated by leptons rather than hadrons. This era would last for about 10 seconds, a brief but important chapter in cosmic history when the stage was being set for the formation of atomic nuclei. Something profound was happening during this time. The ratio of protons to neutrons was being determined. In the intense heat of the earlier epochs, protons and neutrons could easily convert into each other through interactions with electrons, positrons, and neutrinos. But as the universe cooled, these conversions became less frequent. Neutrons are slightly heavier than protons, and in isolation, a neutron will decay into a proton in about 15 minutes. But if neutrons could bind with protons to form atomic nuclei before they decayed, they would be stable. The race was on. Would the neutrons decay away, or would they find protons to bind with? By the end of the Lepton Era, about 10 seconds after the Big Bang, the universe had cooled to about 1 billion degrees. The era of free electrons and positrons was ending. Most of them had annihilated each other, leaving only the small excess of electrons that matched the number of protons. These electrons would eventually be captured by atomic nuclei to form neutral atoms, but that would not happen for hundreds of thousands of years. For now, they remained free, bouncing around in the increasingly diffuse plasma. The universe had taken another step toward the familiar structures we see today. Let us pause and take stock of where we are. The universe is now 10 seconds old. It has expanded from smaller than an atom to about a light year across. The temperature has dropped from unimaginable highs to about 1 billion degrees, still far hotter than the center of the sun, but cool enough that we are entering a regime where matter behaves in more familiar ways. We have protons, neutrons, and electrons, the components of atoms. We have photons, particles of light. We have neutrinos, ghostly particles that barely interact with anything. The cast of characters is assembled. Now it is time for them to begin building the first atomic nuclei. What made these eras possible? The continued expansion and cooling of the universe. Every doubling of the universe's size meant the temperature dropped by half. Every halving of the temperature meant that certain reactions became less likely or stopped altogether. The universe was moving down a temperature ladder, with each rung representing new possibilities and new structures. At higher temperatures, only the simplest particles could exist. As it cooled, more complex structures became stable. This pattern would continue throughout cosmic history, from the formation of nuclei to atoms to molecules to stars and ultimately to life itself. Complexity emerges as the universe cools. Think about the precision required for all this to work. If the forces of nature had been slightly different, if the ratio of matter to antimatter had been even more skewed, if the expansion rate had been faster or slower, the universe might have evolved very differently. It might have recollapsed immediately. It might have expanded too quickly for structures to form. The fact that we exist to tell this story means that the fundamental constants of nature fell within a narrow range that allows for complexity. Some call this fine-tuning and see it as deeply significant. Others see it as selection bias, noting that we can only observe a universe capable of producing observers. Either way, we are fortunate to live in a universe rich with structure and wonder. We have arrived at one of the most important moments in cosmic history. The universe is now between 10 seconds and 20 minutes old. The temperature has cooled to around 1 billion degrees, similar to the core of a massive star. And for the first time, conditions are right for atomic nuclei to form. This process is called Big Bang Nucleosynthesis, and it is one of the great triumphs of modern cosmology. We can calculate exactly what should have happened during these precious minutes, and when we look at the universe today, we find precisely the abundances of light elements that our calculations predict. It is one of the strongest pieces of evidence for the Big Bang theory. What nuclei formed during this era? Let us start with the simplest. A single proton is the nucleus of hydrogen, the lightest element. Hydrogen needs no synthesis. It existed as soon as protons formed. But when a proton and a neutron came together, they could form deuterium, also called heavy hydrogen. When deuterium captured another neutron and another proton, it became helium-4, the nucleus with 2 protons and 2 neutrons. Some helium-3 formed with 2 protons and 1 neutron. Tiny amounts of lithium-7 also appeared. These are the light elements, and they were forged in the first minutes after the Big Bang. Why did nucleosynthesis start with these light elements? Why did the Big Bang not produce carbon, oxygen, iron, and all the other heavy elements we find in nature? The answer is temperature and time. As the universe expanded, it cooled rapidly. By the time the temperature was right for building heavier nuclei, the universe had already expanded so much that the density of protons and neutrons was too low. They were spread too far apart to find each other and fuse. The window for nucleosynthesis lasted only a few minutes. After that, the universe was too cool and too diffuse for nuclear fusion to continue. The forging of heavy elements would have to wait for stars. What were the final abundances? About 75% of the ordinary matter in the universe ended up as hydrogen. About 25% became helium-4. Tiny traces of deuterium, helium-3, and lithium-7 made up the remainder. These ratios are critical. When we observe old stars and gas clouds that have not been enriched by stellar fusion, we find these exact proportions. This agreement between theory and observation is astonishing. It means we truly understand what happened in the first few minutes after the Big Bang. We can look at the composition of the universe and see the fingerprints of those early moments. How do we know these calculations are correct? Because we can test them in multiple ways. We can measure the abundance of deuterium in distant gas clouds. We can measure the helium content of the oldest stars. We can analyze the light from ancient galaxies. Every measurement confirms the predictions of Big Bang nucleosynthesis. Even more remarkably, these predictions depend on the total amount of ordinary matter in the universe. By measuring element abundances, we can determine how much ordinary matter exists. That number matches independent measurements from other sources. The universe is telling a consistent story, and we are learning to read it. Think about what this means. Every atom of hydrogen in your body, every molecule of water, every breath you take contains hydrogen nuclei that have existed unchanged since the first minutes of the universe. When you drink a glass of water, you are consuming hydrogen that is nearly as old as time itself. The hydrogen in water was not created in stars. It was created in the Big Bang. You are literally made of primordial material forged in the cosmic fire at the beginning of everything. Does that make you see your glass of water differently? It should. By the time nucleosynthesis ended, the universe was about 20 minutes old. It had expanded to a few light years across and had cooled to around 100 million degrees. The era of nuclear fusion was over, at least for now. The universe was filled with hydrogen and helium nuclei, along with free electrons and photons. It would remain in this state for hundreds of thousands of years, slowly expanding and cooling, waiting for the next great transition. For now, the nuclei and electrons were kept apart by the intense radiation. But eventually, as we shall see, they would come together to form neutral atoms. The success of Big Bang nucleosynthesis is one of the pillars supporting our understanding of the early universe. Along with the expansion of space, the cosmic microwave background, and the formation of large-scale structure, it provides powerful evidence that the Big Bang theory is correct. We are not speculating about these early moments. We are reading the evidence written in the composition of matter itself. Every star, every planet, every atom tells the same story. The universe had a beginning. It was once incredibly hot and dense. It expanded and cooled. And in those first minutes, it created the raw materials from which everything else would be built. After nucleosynthesis ended, the universe entered a long period called the Photon Epoch. For hundreds of thousands of years, the energy of the universe was dominated by radiation rather than matter. Countless photons, particles of light, filled all of space, bouncing off the free electrons and nuclei in a hot, dense plasma. The universe during this time was opaque, like being inside a thick fog. Light could not travel far before being scattered. If you had eyes during this epoch, you would see nothing but a uniform, blinding glow in all directions. This was the cosmic dark age, not because it was dark, but because no light could travel freely to illuminate structures. Why was the universe opaque during this time? Because free electrons are very good at scattering photons. Every time a photon encountered an electron, it bounced off in a random direction. This meant that photons could not travel in straight lines. They followed random walks, bouncing endlessly from electron to electron. The universe was like a hall of mirrors, with light constantly deflected and redirected. Only when the electrons were captured by nuclei to form neutral atoms would the universe become transparent. And that would not happen until the temperature dropped enough for atoms to remain stable without being immediately broken apart by energetic photons. During the Photon Epoch, something important was happening in the background. The universe was still expanding, and as it expanded, both the matter and radiation were cooling. But they were cooling at different rates. Matter density decreases as the volume grows. Radiation energy decreases even faster because photons lose energy as space expands. This phenomenon, called cosmological redshift, means that the wavelength of light stretches as space expands. Eventually, there came a time when the energy density of matter equaled the energy density of radiation. This moment, occurring tens of thousands of years after the Big Bang, marked the transition from a radiation-dominated to a matter-dominated universe. Why does matter-radiation equality matter? Because it changed how gravity worked in the universe. When radiation dominated, its pressure resisted the pull of gravity, making it hard for matter to clump together. But once matter dominated, gravity could begin pulling matter into denser regions. The tiny density fluctuations created during inflation, which had been frozen in place by radiation pressure, could finally start to grow. This was the beginning of structure formation. The seeds of galaxies began to germinate. Dark matter, which we will discuss more later, began forming invisible halos. The architecture of the cosmic web was beginning to take shape. As the universe continued to expand and cool, approaching 380,000 years after the Big Bang, the temperature finally dropped to around 3,000 degrees. This is cool enough for electrons to be captured by hydrogen and helium, nuclei to form neutral atoms. This process is called recombination, though that is a misleading name because the electrons and nuclei had never been combined before. As recombination occurred, something magnificent happened. With electrons bound into atoms, photons were no longer constantly scattered. Light could finally travel freely through space. The universe became transparent. This moment is called the Epoch of Last Scattering. Imagine what happened. For hundreds of thousands of years, the universe had been an opaque plasma. Then, in a relatively brief period, neutral atoms formed and the fog cleared. Light that had been trapped, constantly scattering off electrons, was suddenly free to travel. That light is still traveling today. It has been stretched by the expansion of the universe from visible and infrared wavelengths to microwaves. We can detect it coming from all directions in space. It is called the cosmic microwave background, and it is one of the most important discoveries in all of science. We will explore it in more depth soon. After recombination, the universe entered what we truly call the cosmic dark ages. Now the name makes sense. With most of the matter locked into neutral hydrogen and helium atoms, and with no stars yet formed to provide light, the universe really was dark. The cosmic microwave background radiation was fading into the infrared and microwave portions of the spectrum, invisible to human eyes. For millions of years, the universe would remain in this dark state, filled with gas but no luminous objects. It was a quiet time, a period of gradual change as gravity slowly pulled matter together, preparing the stage for the first stars to ignite. The Photon Epoch and the Dark Ages represent a long pause in the action of cosmic history. After the dramatic events of the first minutes, the universe spent hundreds of thousands of years simply expanding and cooling, waiting for the right conditions for stars and galaxies to form. But important things were happening during this time. Tiny density variations were growing. Matter was beginning to collect into filaments and halos. The stage was being carefully prepared for the next great act. Soon, perhaps a few 100 million years after the Big Bang, the first stars would ignite and the universe would light up once more. Now we turn our attention to one of the most remarkable discoveries in the history of science. The cosmic microwave background, often called the CMB, is the oldest light in the universe. It is the radiation released when the universe became transparent, light that has been traveling through space for more than 13 billion years. When we observe the CMB, we are literally looking back in time to the surface of last scattering, seeing the universe as it was just 380,000 years after the Big Bang. It is like having a baby picture of the entire cosmos, showing us what the universe looked like in its infancy. The CMB was predicted before it was discovered. In the 1940s, physicists realized that if the universe had been hot and dense, it should have been filled with thermal radiation, and that radiation should still be detectable today, cooled by cosmic expansion to just a few degrees above absolute zero. But it was not until 1964 that two scientists, Arno Penzias and Robert Wilson, accidentally discovered a persistent microwave noise in their radio antenna. They had found the cosmic microwave background. For this discovery, they won the Nobel Prize. It was direct evidence that the Big Bang really happened. What makes the CMB so important? It gives us a direct view of the early universe. The photons we detect in the CMB have been traveling unimpeded since recombination. They carry information about conditions at that time encoded in their temperature and polarization. When we measure the CMB carefully, we are reading a message written in light by the infant universe. That message tells us about the density of matter, the geometry of space, the nature of the initial fluctuations, and much more. The CMB is a treasure trove of cosmological information, and scientists have been mining it for decades. At first glance, the CMB appears almost perfectly uniform. Its temperature is 2.7 degrees above absolute zero in every direction we look. This uniformity is itself significant. It tells us the early universe was remarkably smooth and homogeneous. But when we measure more carefully, using sensitive instruments, we can detect tiny temperature variations, differences of only a few 100,000ths of a degree. These tiny fluctuations are crucial. They represent the density variations that would eventually grow into galaxies and galaxy clusters. Without these fluctuations, the universe would have remained smooth and featureless forever. Why are there fluctuations in the CMB? 3. Remember inflation? The quantum fluctuations that were stretched to cosmic size during inflation created regions of slightly different density. These density variations caused temperature variations in the plasma of the early universe. Hotspots correspond to regions that were slightly denser, where gravity pulled matter together and heated it. Cold spots correspond to regions that were slightly less dense. When recombination occurred and the CMB photons were released, these temperature variations were frozen into the radiation. They have been traveling toward us ever since, carrying a record of those initial quantum fluctuations. The pattern of fluctuations in the CMB is not random. It has a characteristic scale, a preferred size for the hot and cold spots. This scale corresponds to the distance that sound waves could travel in the plasma before recombination. Yes, sound waves. In the early universe, pressure waves propagated through the plasma, creating oscillations in density and temperature. These acoustic oscillations, like cosmic musical notes, created a characteristic pattern that we can observe in the CMB today. By analyzing this pattern, we can determine fundamental properties of the universe, including its age, composition, and geometry. Multiple space missions have been launched to study the CMB in exquisite detail. The COBE satellite first detected the fluctuations. The WMAP satellite mapped them precisely. The Planck satellite achieved even greater precision, measuring temperature variations to millionths of a degree. Each mission has refined our understanding of cosmic history. The data from these missions has allowed us to determine the age of the universe to within 1% accuracy, to measure the amounts of ordinary matter, and dark energy, and to test the predictions of inflation. The CMB is the Rosetta Stone of cosmology. When you look at an image of the cosmic microwave background, you are seeing further back in time than anything else we can observe. You are seeing light from before stars existed, before galaxies formed, before planets and life were even possible. You are witnessing the universe in its infancy, just emerging from the hot, dense conditions of the Big Bang. And remarkably, that infant universe already contained within it the seeds of everything to come, including you. The tiny fluctuations visible in the CMB would grow over billions of years into the rich tapestry of structures we see today. The past and present are connected. We have mentioned the expansion of the universe many times, but now let us explore what this expansion really means. This is one of the most profound and counterintuitive ideas in all of science. Space itself is expanding. Not objects moving through space, but the very fabric of space growing larger. Imagine a stretchy sheet with coins glued to it. As you stretch the sheet, the coins move apart, not because they are sliding across the surface, but because the surface itself is expanding. Galaxies are like those coins, carried apart by the expansion of space between them. The discovery of cosmic expansion is one of the great achievements of 20th century science. In the 1920s, astronomer Edwin Hubble observed that distant galaxies are moving away from us, and the farther away they are, the faster they are receding. This relationship, called Hubble's law, can only be explained if space itself is expanding. When Hubble announced his findings, it revolutionized our understanding of the universe. The cosmos was not static and eternal, as had been assumed. It was dynamic, growing, evolving. And if it was expanding now, it must have been smaller in the past. How do we know galaxies are moving away? Through the Doppler effect. Just as the pitch of a siren changes as an ambulance moves toward or away from you, the wavelength of light changes when its source moves. Light from an approaching object is shifted toward shorter, bluer wavelengths. Light from a receding object is shifted toward longer, redder wavelengths. When we observe distant galaxies, their light is redshifted. The amount of redshift tells us how fast they are receding. And when we plot recession velocity against distance, we find a linear relationship. The farther a galaxy, the greater its redshift. This is the signature of cosmic expansion. One of the most common misconceptions about cosmic expansion is that galaxies are flying through space away from us. This makes it seem like we are at the center of some cosmic explosion. But that is not what is happening. Space itself is expanding uniformly everywhere. From any galaxy's perspective, all other galaxies appear to be receding. There is no center to the expansion, or more accurately, every point is equally the center. Imagine an infinite sheet of graph paper where every square doubles in size. From the perspective of any square, all other squares are moving away, but no square is special. That is what cosmic expansion is like. The expansion of space has profound implications. It means the universe has a history. If space is expanding now, it was smaller in the past. Extrapolating backward, we arrive at a moment when all of space was compressed to a point. It's the Big Bang. The expansion also means the universe has a future. Will it expand forever? or will gravity eventually halt the expansion and cause everything to collapse back together? For decades, scientists debated this question. The answer depends on the total density of matter and energy in the universe. If density is high enough, gravity will win. If not, expansion will continue eternally. In the late 1990s, scientists made an astonishing discovery. By observing distant supernovae, they determined that the expansion of the universe is not slowing down as expected. It is accelerating. Galaxies are moving apart faster and faster. This was completely unexpected. Something is pushing space apart, working against the attractive force of gravity. Scientists call this mysterious influence dark energy. We do not know what it is. It might be a property of space itself, a cosmological constant as Einstein once proposed. Or it might be a dynamic field pervading the universe. Whatever it is, dark energy makes up about 68% of the total energy of the universe. The accelerating expansion means the universe will continue to grow forever, becoming ever more diffuse and cold. In the distant future, galaxies beyond our local group will recede so far that their light will never reach us. The observable universe will shrink even as the actual universe expands. Eventually, only our own gravitationally bound cluster of galaxies will remain visible, surrounded by darkness. This is the ultimate fate cosmologists call the Big Freeze or heat death, when the universe reaches maximum entropy and no useful work can be done. But that lies trillions of years in the future. For now, we live in a golden age when stars shine and life flourishes. The expansion of space also affects how we think about distance and time in cosmology. Light from distant objects has taken billions of years to reach us, so we see those objects as they were in the past. But during that time, space has been expanding, so the object is now farther away than it was when the light was emitted. This means we must distinguish between different kinds of distance. The co-moving distance accounts for expansion and tells us where an object is now. The light travel distance tells us how far the light has traveled. These distinctions matter when we try to map the universe accurately. We have explored the story of the Big Bang in detail, but you might wonder how confident we can be in this story. Is it speculation, or is it supported by solid evidence? The answer is that the Big Bang theory is one of the most thoroughly tested and confirmed theories in all of science. Multiple independent lines of evidence all point to the same conclusion. The universe had a hot, dense beginning and has been expanding and cooling ever since. Let us review the key pieces of evidence that have convinced scientists the Big Bang really happened. First, and most directly, we have the expansion of the universe itself. As we have discussed, Edwin Hubble discovered that distant galaxies are receding from us, and the farther away they are, the faster they recede. This observation can only be explained if space itself is expanding. When we trace this expansion backward in time, we arrive at a moment about 13.8 billion years ago when the universe was infinitely dense and hot. This is not speculation based on theory alone. It is a direct inference from observation. The universe is expanding now, therefore it was smaller in the past. Second, we have the cosmic microwave background radiation. As we explored earlier, the CMB is the thermal radiation left over from the moment when the universe became transparent. It has exactly the properties we would expect if the universe was once a hot, dense plasma. Its temperature is uniform to 1 part in 100,000, except for tiny fluctuations that match predictions from inflation and acoustic oscillations. No alternative theory can explain the CMB as well as the Big Bang. It is direct observational evidence of the hot early universe, and its detailed properties confirm numerous predictions of Big Bang cosmology. Third, we have the abundances of light elements produced in Big Bang nucleosynthesis. As we discussed, the first few minutes of the universe forged hydrogen, helium, deuterium, and small amounts of lithium. We can calculate exactly how much of each element should have been produced based on the conditions in the early universe. When we then measure the abundances of these elements in old stars and gas clouds that have not been contaminated by stellar fusion, we find precisely what the calculations predict. This agreement is stunning. It means we truly understand the nuclear physics of the first minutes after the Big Bang. Fourth, we have the observed evolution of galaxies over time. Because light travels at a finite speed, when we look at distant objects, we see them as they were in the past. By observing galaxies at different distances and therefore different times in cosmic history, we can watch how galaxies have evolved. What we see matches Big Bang predictions. Distant galaxies are smaller, more irregular, and have more active star formation than nearby galaxies. The universe has been evolving from a simpler, more chaotic state to a more structured, mature state, exactly as the Big Bang theory predicts. Fifth, we have the large-scale structure of the universe. Galaxies are not randomly distributed. They form filaments, walls, and clusters surrounding vast empty voids, creating a cosmic web. This pattern matches what we expect if structure grew from tiny initial fluctuations through gravitational collapse, starting from the density variations we see in the CMB. Computer simulations of structure formation, starting with Big Bang initial conditions, produce cosmic webs that look remarkably like what we observe. The universe's architecture tells the story of its growth from quantum seeds planted during inflation. Sixth, all of these independent lines of evidence point to the same age for the universe, about 13.8 billion years. We can estimate the age from the expansion rate, from the oldest stars, from the cooling of white dwarfs, from radioactive dating, and from the properties of the CMB. All these methods, which use completely different physics, give consistent results. This consistency is powerful confirmation that we understand cosmic history correctly. The universe is not infinitely old. It had a beginning that we can date with precision. No scientific theory is ever proven beyond all doubt. Science is always provisional, always open to revision in light of new evidence. But the Big Bang theory is supported by such a wealth of evidence from so many different sources that scientists consider it essentially established. Alternative theories, like the steady-state model that was popular in the mid-20th century, cannot explain these observations. The Big Bang theory successfully predicts what we observe, makes sense of the universe's properties, and has been confirmed in detail by precision measurements. We can be confident that the broad outlines of the story are correct. We have journeyed from the very beginning of time to the present day. We have witnessed the birth of space and time, the separation of forces, the formation of matter, the creation of atoms, and the emergence of the cosmic structure we see today. But what does it all mean? Why should you care about events that happened billions of years ago in conditions utterly unlike anything in our everyday experience? I believe the Big Bang story matters profoundly, not just scientifically, but philosophically and emotionally. It changes how we see ourselves and our place in the cosmos. First, the Big Bang tells us that we are part of a story much larger than ourselves. You are not separate from the universe. You are made of atoms forged in the Big Bang and in stars. You are a temporary pattern of matter and energy, a way the universe has organized itself to become conscious and self-aware. When you look up at the night sky, you are not looking at something foreign and distant. You are looking at your cosmic ancestry. The universe is your home, not just the planet you live on, but the entire cosmos, extending billions of light years in all directions. You belong to this vast, ancient story. Second, the Big Bang confronts us with our cosmic smallness, and yet simultaneously with our significance. In terms of space and time, we are incredibly small. Our entire recorded history spans a few thousand years. The Big Bang happened 13.8 billion years ago. We live on a tiny planet orbiting an ordinary star in one galaxy among hundreds of billions. And yet, we have figured this out. Beings made of star stuff have decoded the origin of the universe itself. We may be small, but we are not insignificant. We are the universe's way of knowing itself. Third, the Big Bang reveals a universe that is fundamentally creative and evolutionary. The universe did not spring into existence complete and finished. It started simple and grew complex. From formless energy came particles. From particles came atoms. From atoms came molecules. From molecules came stars and planets. And from those came life and consciousness. Complexity and order emerged from simplicity through natural processes operating over vast spans of time. We are part of an ongoing creative process, the universe continuing to explore what is possible. You are creativity itself, happening right now. Fourth, the Big Bang shows us that the universe is comprehensible. The fact that we can understand the first moments of cosmic history, that we can describe them with mathematics and test our ideas with observation, is profoundly meaningful. The universe did not have to be this way. It could have been chaotic and random, beyond our ability to understand. Instead, it follows rules, patterns, mathematical laws that our minds can grasp. Why should mathematics, a product of human thought, describe physical reality so perfectly? This deep connection between mind and cosmos is one of the great mysteries. Fifth, the Big Bang invites us to think about the biggest questions. Why is there something rather than nothing? Why does the universe have the properties it has? Are there other universes with different laws of physics? Is our universe inevitable or a cosmic accident? These questions push us to the boundaries of science and into the realm of philosophy and metaphysics. We may never have complete answers, but the act of asking deepens our humanity. It connects us to every culture that has looked up at the stars and wondered about origins and meaning. The Big Bang also teaches us humility. Despite all we have learned, there is still so much we do not know. We do not fully understand the first moment of time. We do not know what caused the universe to begin. We do not know what most of the universe is made of. Dark matter and dark energy remain mysterious. We do not know if our universe is unique or one among many. Science has revealed vast territories of knowledge, but also vast territories of ignorance. This should make us humble about our understanding while keeping us curious and motivated to learn more. Finally, I believe the Big Bang offers us a source of meaning and connection in an often confusing world. When you feel isolated or lost, remember that you are part of this grand cosmic story. The atoms in your body were forged in the Big Bang and in stars. You are billions of years old and yet brand new. You are the universe becoming aware of itself, if only for a brief moment. Life is rare and precious. Consciousness is a remarkable gift. And now you know where it all came from. You have looked back to the beginning and seen how everything started. Carry this knowledge with you. Let it fill you with wonder. Our journey to the beginning of time is complete. We have traveled back 13.8 billion years and witnessed the birth of everything. We have seen how the universe expanded from unimaginable conditions to become the vast structured cosmos we inhabit today. Every star you see, every breath you take, every thought you think is connected to that first moment. You are not separate from the Big Bang. You are its continuation, the universe exploring itself through consciousness. If this story has moved you, if it has changed how you see the world even slightly, then we have achieved something meaningful. Keep looking up, keep wondering, and remember, you are made of stardust.